All right, so are we ready to start?
I'm ready.
All right. Well, I will let whoever has this one done start working on it, on typing it in or writing it up or whatever. And when you're doing this one, there's going to be multiple steps, so be sure to write all of them down so we kind of can follow what you've done along the way. So does anybody have any clues on how to get this one done, or where are we at with this?
It should be up there now. Can you not see it?
Oh, now it just popped up. It took a while, I guess. All right, so what she did, it looks
I don't
like,
have the final answer like calculated out yet, just because I haven't
okay,
my calculator yet.
all right. So 5x ln 10 equals 5x minus ln 7. And then you took 5x ln 10 minus 7 times ln 10, 5x ln 7, and then move the extra one side. Yeah, I think that looks like it should be good. So then calculator's the only thing, and then if you get the calculator, what you should get, I'll write that part
It's
down.
5.76455699.
Yeah, so I think this one, they just want it rounded usually on this kind of 4 decimal places. So we'll put 7646. So that would be your answer. So yeah, so the first thing you have to do is you have to take the ln of both sides. And then when you do that, you can pull it down your exponent. And then after that, it's just a matter of distributing the exponent times the ln of that 10 on the other side of the 7. And then getting all your x terms on one side, the number parts on the other side, factoring out your x, and then dividing by that number that's left over. And then you get your final value there. So anybody have any questions or concerns about that one? All right. How about this one? So here we're going to take the half-life of strontium 90 is 28 years, and how long will it take for a 40 milligram sample to decay to a mass of 10 kilograms? So I guess I should say, the first thing you need to do is determine your K value. And because of that, we already know it's a half-life, so it's pretty easy to determine the K value for that. And then you plug that into the exponential decay function and use your initial amount and your final amount. And then after that, you can solve for your T years, how long it's going to take to decay that long.
Is this from 4.7?
I think this one's still 4.6. Let me check here. It's one of those, once you get to 4.7, basically it's everything up to that point is in 4.7. And so it's just different application problems. So, technically you could call it 4.7, but it comes out of the material out of 4.6. And so I think that's why it looks familiar. And looking back, really, you could even go back to 4.1 on this one too. So it's kind of a mixture of everything just all together.
Am I on the right track with that?
Yeah, so far you're doing fine. So that gives you your K. Now you have to plug that into the exponential formula with your initial and your final mass. I think, Madeline, one thing here, plugging it all the way back here, this is a special case where this is half. Now, you can also just use the formula K equals minus ln of 2 over the half-life, and sometimes it's capital T, sometimes it's little, depending on how they do it. And so then we could have gone straight to the ln of 2 over 28, and we would have got our negative 0. What was it? You got it up there, 0.24755 or something like that. And so then we take that and plug that into here. And so then we would have the 10. Well, I guess I see what you did. You did half. Okay, with this, I was thinking you used the 10. Never mind. So yeah, you're fine. Now just put your 10 in this equation, and then you're going to make that T. This is the K from there that we solve for. And so now
So
we
we
just
just plug in 10 for the Y. I was just following an example from class. That's all I was doing.
Yeah, so that there's different stages that we kind of went through. One of them where we've had this formula so we could get directly to the K. Another one where we said, okay, well, this is the initial amount, half of it is this, and then we kind of calculated it down until we got the same formula. Because if you think about that, that's the ln of 2 to the negative 1 if you do that, and then that comes down, so that's minus ln of 2 over the t. And so that's your half-life. And then what you do is you just plug everything back in now with the final mass, 10, the original, and then it's e to the, now we have a negative 0.024755 times t. And now that's what we're going to solve to find out what it is, the time to get down to all the way to 10. And so now you just have to do that, basically the same things you did here, but now we do it and solve for t.
Okay, that makes sense.
Yeah, and I totally was thinking, all of a sudden I was like, oh wait, she plugged it all the way to the back, the first one, and then I forgot that we are going to 10 instead of a half. So yeah, so what you did is fine to get to your K, and then, or if you didn't, that's probably the easiest if you don't remember basically this formula to get the K or the half-life. And so with this formula, if you know K, you can find the half-life. If you know the half-life, you can find K. And so that goes both ways. And so in our case, we used it to find K. And then we plugged it all back into the original equation here. But now we're going down to the 10. And now we don't worry about the half-life because we want to solve for T. And we use that K that we found there. Yep, that looks good. So it takes 56 years to do it. And on this one, this is kind of a special case because if you think about that, half-life is 28 years. So half of 40 gets us down to the 20, and then 10 is half of that one. So then that's another half-life. So really it's the 28 times 2, which is 56. But this is, if I required you to submit all your work on the test, this is the way you would want to show it. That way I could see how you got to that 56 years. But yeah, this is the correct way to do that. All right, so this one, it can be either from 4.1 or 4.7, kind of depending on how you want to look at it, because in 4.1 we started with some interest and things like that kinds of problems, so we were introduced to the formula we need to use. Then 4.7, we kind of, were able to do more of the solving it based on all the different log functions we had, because when we first had it, they gave us everything and we just solved for a, which is the how much is after so many years. And now we know how to use it and solve for any of the variables using the log functions. So does anybody remember the formula we need to use?
It's kind of annoying to type out, but I know it.
All right, so how about I write it for you, and then that'll give you one step, but it won't be on the test, so you'll have to know it. So it's a of t is equal to a sub 0 times 1 plus r over n, all to the n times t. So, a0 is the principal that you put into the account. The rate in decimal form, n is going to be depending on how often it's compounded. And then the t is how long it's going to be compounded for, so 2 years, 5 years, whatever. And then this is going to be your kind of your final amount that it grows to after we plug all those values in. So this one, what it does is it tells you you have to solve for t, and so you are given everything else here, and so now you just have to use log functions and stuff like that to solve for it. All right, so that one looks good as well. And then if we do that to the 2 decimal places, it's just going to be 9.16. So then that would be, your years. I think this is years. Yeah, years. Okay. So that's how you would work this one. Again, you just have to remember this equation. And the other only key thing is knowing the n values. So quarterly means it's going to be 4 times. Annual, that would be 1. Semi-annual would be 2. Monthly would be like 12. Daily would be 365. So it kind of depends on how often they compound it is going to depend on what your n value is. But everything else is pretty straightforward plugging that in there. All right, so this one is from 4.7, but again, it's kind of like the previous one we did, which was kind of 4.641. So it could be any of those. And so basically, you're going to look for your K first, and then after that, plug it back into your equation, and then solve for your actual time to get it down to the 2 milligrams.
So is this kind of the same as the other one that we just did, number 10, 9?
Yeah, pretty much. The other one, it kind of was one where, like I said, you were kind of to know that if you had um, oops, the uh, K is equal to the negative ln of 2 over the half-life. Now this one, it doesn't give you the half-life, so this one you have to work like you did the last one, and then that will give you the K, and then you can do it the whole thing again, and then figure out what it is for the 2 in this case. So the, like I said, a lot of the questions are about the same for the um, different sections and different this chapter, but just different applications as far as what part do you know at what point. So like when we were doing the previous one, we only knew how to do this. The next one, we knew how to plug things in on both sides and work our way down. So it's a little bit different. So that's why, it's still a decay, because, those are pretty famous log types of things. The other one, we could do a growth, and so you'd have a growth function instead of a decay kind, so it'd be doubling. And so instead of a negative here, you'd have a positive for the doubling, and you'd figure that out. Or you could do, again, the initial and the final here, and then solve for your K, then plug it in to figure out when it was going to reach some determined amount that you had to have, and then solve for your T that way. So
Is that right so far?
I think it looks good. So yeah, it's all good. So yeah, it's good. It just I want to see what the answer is to the K. That's going to be depending on if it's right or not. So
Wait, what do you mean? What's my answer to K? Isn't that K? Or do I need like a more specific number?
well, I mean,
I
you can
usually wait till
use
the end to do that.
this as far as your thing, and then
It's
when
just
you plug it back in, then you're just gonna have something bigger. So I personally, I would probably say that's the most correct answer. That's the accurate answer as far as it's the exact. And then if you did, the approximate, then you would have a negative 0.02433. And then depending on how far you went out, there's 1162 also. But again, that would probably be the best thing if you were able to plug that into your calculator as you went in back in, because then what you're going to have to do is plug that K back in here and then solve for the T afterwards.
I have the rest of it written out. I just haven't typed it up yet.
Yeah, that's fine. Yeah, so yeah, that up to that point it's perfect. So
It keeps cutting off my stuff a little bit.
that's okay. I'll go ahead and add it for you. There's a T here, a T here. that looks good. So again, we had to go back to our original, formula for the exponential decay or growth, depending on what you had. Plug in one set of data and along with the initial time. So you'd have your 7.25 is where we're going down to. Initially started at 13, and our time from 0 to the 7.25 was the 24. Work our way down through all the log stuff, get this value, or keep it as a whole exact value like she did here. And then you plug it back into the original equation, and now we want to go down to 2, so we plug in a 2 here instead of the 7.25. We have our new k value, and then we're solving for t, so we just use logs of that. So we take the ln of both sides, bring down that whole big long thing times t, then ln of e is just 1, and then divide by that big long thing like she says here, and then you get like 76.9 something, and to the nearest minute is going to give you the 77 minutes. Any questions on that one? All right, so the last one is write an expression of the type, and this is what it gives us. Now, I saved this one for last because I was trying to figure out why, when I did the printout, it lost some of the stuff. And what it did is it lost the base, and I liked it better with the C here because we learned it was C. And so I kind of programmed mom for this problem, so it would actually make sure it kept the 3 in or whatever value it is for whatever base we're doing every time, and then I converted it to the C here, so then it gives you this now instead of what it shows on your expression, because before it just said a log and then x plus b, but it never gave you the base, and without knowing that base you really can't solve this easily, and it's going to be really complex. But when it gives you the base, this problem becomes a lot easier. So I'll let you work on this one. And I guess the only hints on this one would be look at your vertical asymptote and then kind of look at, reflections, moving up, down, left, right, things like that. But the nice thing here is says it doesn't give us a D. So we're not worried about moving up and down. All we're worried about doing is moving left and right and then stretching it. So those are the only key things to worry about here.
What section would this have been in?
This is back in 4.4, and we skipped over 4.4 just because, like I said, I was trying to figure out how to get it to program mom to make it do what I'm showing you here now. So it took a while to get there, so that's why I put it way off the last, but this is 4.4. Any thoughts or anything on this one yet, or?
I don't really know how to do it with it being log of 3.
All right, so the log of 3 really helps you. That's actually the most helpful part here. If we just had log base 10, that doesn't help us, and that's why I had to figure out why it wasn't putting that in there. So looking at this, what do we know? Let's first draw log base 3. So we know for log functions, we always have the point 1, 0. I'll draw a dot there. The 1, 0. And then we have whatever that base is, then it's going to be 3, 1. It's going to be b comma 1. And so that's going to be kind of what we have for our initial plot. So that's what it would look like, roughly drawn. So the other thing we notice is for our new graph that this is our vertical asymptote, x equals 3. Okay, so what do you know about the x equals 3 as a vertical asymptote? That means we've shifted from x equals 0, which is where it used to be here, to x equals 3. So we've moved right 3. So that tells us then we have y equals a log base 3 of x minus 3. Okay. Now what do we think about? Well, now we look at and see what does the original graph look like compared to our new one. Well, if we can imagine, if we would flip this over the y-axis and put, this one here, and then we put the -3 one here, and so we would come up like that. Now we have this similar shape. It's not stretched like it should be, but we at least have the similar shape to what that is. And so that means we're going to flip across the y-axis, so we have to take a negative of what's in here. So that's our next part. And so we're going to take a negative of the x minus 3. And so to simplify that, we get a log base 3. And now that's a negative x, and that's plus 3. Okay. So that's that. Now what do we do? Well, now we have some points. And so what we're going to do is we're going to plug in one of the points. And if you remember, we can't plug in the one with the intercept here. And so what we're going to have to plug in is this one here. We're going to have to plug in that point because that's the only one we can do. We can't do that one. And so we have to plug in the y-intercept. And so that's going to be a 3 for y, then a, then log base 3. X is 0, so minus 0 is still 0, plus 3. So now it gives us 3 equals a log base 3 of 3. Now what do we know about log base 3 of 3? Well, that's just 1. And so we get a is equal to 3. And so now if we bring all that together, if we go and put this in, so we're at this point, so now we can say, well, y equals 3 log base 3 of negative x plus 3. And that then is going to be our expression in this form for the transformation based on what we have here. And so we're stretching it by 3. So if we multiplied, by 3, it's not exactly how it's supposed to be, but mathematically that's the way it's going to look. It's with all the stretching and changing things left and right here, because we're going to have to move this one up 3, and then when we reflect it over, it comes over here to the -3, and then when we move it over to the right, we're at that 3 zeros. So we have to do all this stuff based on this one, not on this one. So that's why we multiply that one by 3, we get up to the 3, and then we reflect over the y-axis. So we come over here to the -3, 3, and then when we move it over to the right 3 units because of our shift here, then that gives us our point there. And so that fits our graph model. And so that's kind of how I would do it. First, you kind of have to figure out your shift, and then you plug that in to here. And then after that, you have to decide, well, is it reflecting over the y-axis? Maybe maybe the one you'll get reflects over the x-axis, which in that case, it's going to be a negative out here. And then you'd have your x minus 3 still there. And then again, you just find some other point besides the x-intercept to put on there, and then you solve and you get your a value. and then you plug that in, and you should have your full equation.
What if it wasn't like an easy one, like how it's log base 3 of 3 is just
Well, see, that's the thing. It's supposed to.
complicated?
It's going to be an easy one. The way it's programmed, you might have log base 5 of 5, or it's going to be one where you can do it. But don't forget, you can solve log base 3 of 5, because then you just take log of 5 over log of 3, and so that would then be what a would be equal to. So, or if you had like 3 on the left, say maybe you had 3 equals a log 3 of 5, then what you're going to have to do is you're going to have to divide by log base 3 of 5, divide by log base 3 of 5. And if you need a number, then you just have to break that log base 3 of 5 into this. And so you're taking 3 divided by whatever that is. Or if you multiply by the reciprocal, it'll be 3 times log base 3 of 3, or log of 3 over log of 5. So it's doable still. You just have to remember the change of base formula and do something like that. So even if it doesn't give you a nice thing, it's still nice now that we know, the change of base formulas, and we can solve it that way. But before, you were having to try to figure out what that value there was, and that was the part that was hard, because you didn't know where your original graph was going through, because it didn't tell you what that point was. But then once it plugs in and gives you, the base, then you know what that b comma 1 point is, and then you can check everything and make sure everything works as after you're done, to see what you have there. So any other questions? All right, well, if not, our time is up, so I will let you go, and I will see you next week for the final. If you have questions along the way, just send me an email, and I can try to help you that way. Or if need be, we can have a Zoom session or something, and try to get that if I'm not doing a proctoring another exam.
It's on Monday, right?
I believe that's what we decided on. Wasn't it at 9 a.m. on Monday? I forget. I have so many tests going on right now. I forget what class is which one right now.
It's 3.
3? Okay. Yeah, 1 o'clock is my 900 class. So yeah, so it's 3 then. All right. Then I will see you then.